LT3755 High Side Sense LED Controller for High Current LED Applications by Linear Technology. Welcome to the training module on LT3755. Today's training outline consists of features and application, block diagram, application information, dimming control, and application circuit. The LT3755 and LT3755-1 are DC-to-DC controllers designed to operate as a constant current source for driving high current LEDs. The LT3755 uses an external N-channel MOSFET and can drive up to 14 1-amp white LEDs from a nominal 12-volt input, delivering in excess of 50 watts. It incorporates a high side current sense, enabling it to be used in boost, buck boost, or SEPIC, and flyback topologies. The LT3755 can deliver efficiencies of over 94% in boost mode, eliminating any need for external heat sinks. The LT3755 uses true color pulse width modulation dimming, which delivers constant LED color with dimming ranges of up to 3000 to 1. Two versions of the LT3755 are available. The standard LT3755, which offers an open LED status pin, and the LT3755-1, which replaces the open LED status pin with a frequency synchronization pin. The device's 4.5 volts to 40 volts input voltage range makes it ideal for a wide variety of applications, including automotive, industrial, and architectural lighting. The LT3755 is a constant frequency current mode controller with a low side N-type metal oxide semiconductor gate driver. The gate pin and pulse width modulation out pin drivers and other chip loads are powered from INT VCC, which is an external regulated power supply. In normal operation, with the pulse width modulation pin low, the gate and pulse width modulation out pins are driven to ground. The VC pin is high impedance to store the previous switching state on the external compensation capacitor, and the ISP and ISN pin bias currents are reduced to leakage level. When the pulse width modulation pin transitions high, the pulse width modulation out pin transitions high after a short delay. At the same time, the internal oscillator wakes up and generates a pulse to set the pulse width modulation latch, turning on the external power MOSFET switch. The LED current is programmed by placing an appropriate value current sense resistor between the ISP and ISN pins. Typically, sensing of the current should be done at the top of the LED string. The control pin should be tied to a voltage higher than 1.1 volts to get the full-scale 100 millivolts threshold across the sense resistor. The control pin can also be used to dim the LED current to 0. Although relative accuracy decreases with the decreasing voltage sense threshold, the LED current programming feature can increase total dimming range by a factor of 10. The control pin should not be left open. FB is intended for constant voltage regulation or for LED protection or open LED detection. In normal condition, the current loop dominates and the exact output voltage is less than the setting through FB. Do not leave the FB pin open. If not used, connect to ground. For a boost application, the output voltage can be set by selecting the values of R1 and R2 as shown in the figure. For a boost-type LED driver, set the resistor from the output to the FB pin such that the expected voltage FB during normal operation will not exceed 1.1 volts. For an LED driver of buck or a buck boost configuration, the output voltage is typically level shifted to a signal with respect to ground as illustrated in the bottom figure. There are two methods to control the current source for dimming using the LT3755. One can control by using control pin to adjust the current regulated in the LEDs. A second method uses the pulse width modulation pin to modulate the current source. One area where these LED drivers especially excel is in the performance and flexibility of their pulse width modulation dimming capabilities. The pulse width modulation dimming method is straightforward. The LED is driven by a tightly regulated current for a fixed internal in every pulse width modulation period. During the off phase, the current in the LED is 0. During the on phase, the current is carefully regulated. The minimum pulse width modulation on or off time will depend on the choice of operating frequency through the RT input. For best results, or for best current accuracy, the minimum pulse width modulation low or high time should be at least 6 switching cycles. Maximum pulse width modulation period is determined by the system and is unlikely to be longer than 12 milliseconds. The maximum pulse width modulation dimming ratio can be calculated from the maximum pulse width modulation period and the minimum pulse width modulation pulse width. This slide offers application information on LT3755. For example, the selection of the input capacitor, output capacitor, and soft start capacitor. An X7R type ceramic capacitor is used as the input capacitor. It is usually recommended since it has the least variation with temperature and DC bias. The value can be calculated based on the given equation. The selection of the output capacitor depends on the load and converter configuration. For LED applications, the equivalent resistance of the LED is typically low, and the output filter capacitor should be sized to attenuate the current ripple. Use of X7R type ceramic capacitor is recommended. The LT3755 has a soft start option for which a capacitor needs to be connected. For many applications, it is important to minimize the inrush current at startup. The built-in soft start circuit significantly reduces the startup current spike and output voltage overshoot. The soft start interval is set by the soft start capacitor selection according to the equation as shown. Typical value of 0.01 microfarads is used. This slide offers information about inductor selection and sense resistor selection. The inductor used for LT3755 is given here, and it should be chosen based on operating frequency, input, and output voltage, which will provide current mode ramp sense. The sense resistor is connected between the source of external N-type MOSFET and ground to provide adequate switch current to drive the application without exceeding the current limit threshold on the sense pin of the LT3755. In buck mode configuration, the sense resistor should give a switch current at least 30% greater than that required LED current. For buck boost and boost configurations, the resistor can be estimated using the equations as shown. This is a typical application of LT3755, which is an 8-watt buck mode LED driver with 50:1 pulse width modulation dimming at 20 kHz and 90% efficiency. This circuit shows a buck mode converter that regulates a 16-volt LED string at 500 milliamps from a 22-volt to 36-volt supply. It has an external charge pump and level shift to drive the gate of an LED disconnect N-type metal oxide semiconductor. This level shift provides much faster rise and fall times than the familiar resistor level shift driving a P-type metal oxide semiconductor, and uses much less current. It is clear that the output LED current has no perceptible variation as pulse width is smoothly adjustable between the minimum on time and minimum off time. The efficiency of this 8-watt circuit exceeds 90%. This typical application circuit shows a SEPIC converter driving a 1 amp 20-volt LED string from a 10-volt to 36-volt supply. In addition to providing step-up and step-down capability, this circuit is handy because it provides input-output isolation and built-in protection from short to ground on the output. The efficiency of this circuit exceeds 87%. The minimum efficiency combined with its excellent thermal management capability enables it to deliver up to 240 watt output power without a heatsink or forced airflow. Our last slide shows a typical application of LT3755, which is a 21 watt buck boost mode with a 250 to 1 pulse width modulation dimming and open LED protection.